let's take a look at how we can prove that something is an equivalence relation with an example. Let's suppose we want to show that x arrow y is an equivalence relation where we have between two integers if 2x plus 8y is congruent to 0 mod 10. Okay, well, we need to check, we're going to check the different properties of this. First of all, let's list out what properties we're looking for it to be an equivalence relation. It needs to be reflexive, needs to be symmetric, and it needs to be transitive. Now, if it is an equivalence relation, it'll chunk up the integers into pieces. It'll partition them into distinct parts. So let's take a look and see how we can do that based off of these ideas. And then after that, we'll see how we could actually realize that it's an equivalence relation because it partitions the integers by way of just being into fibers of a particular function. But right now, let's take a look at these properties and see how we can work with that. What does reflexive mean? That means that x arrow x, okay, no matter what x is, that'll work. Well, that's pretty clear because if we replace y with x, then we get 2x plus 8x, that's 10x, and of course that's equivalent or congruent to 0 mod 10. So we have reflexivity. What about being symmetric? So that means that if x arrow y, then we'll have y arrow x. Okay, so do we have this happening? Well, to see that, let's take a look at this statement right here. What would happen if I took this and I just multiplied it by negative 1 on both sides? We'd get negative 2x, negative 2x minus 8y is congruent to 0 mod 10. Now I want you to look at this for a minute. Negative 8 is actually congruent to, is congruent to positive 2 mod 10. It's 2y, and I'll write it over here, 2y. So I wrote it right over here. Negative 2 is congruent to 8 mod 10. So just write it over here. Oh my goodness. So it looks like, hey, that looks like the exact same statement as we had before. So in other words, y of course will be going to x, and under the assumption that x was going to y. All I did here was take this and multiply it by negative 1 in mod 10, both sides of this congruence, and I was able to, and rewriting the negative 8 and negative 2, I was able to see this pretty quickly. So yes, it is symmetric. Okay, now what about transitivity? This means that if x goes to y and y goes to z, then that will imply, so if both of these things happen, that will imply that x will have to go to z as well. Okay, so let's take a look and see how I want to do that. So we're going to be assuming that, okay, let's just write out what we're assuming. We're assuming this, 2x plus 8y is congruent to, and now we can even write it right here. They're all going to be congruent to 0 mod 10. So let's see, 2y plus 8z, and that's congruent to 0 mod 10. Okay, so we have, okay, so we have this. We know 2x plus 8y is congruent to 2y plus 8z, which is congruent to 0 mod 10. And we want to show that 2x plus 8z is congruent to 0 mod 10. Okay, so that's a question mark. Do we have this? Well, let's think about this for a minute. 8y, another way of thinking about 8y is thinking of it as negative 2y congruent to mod 10. This 8 is negative 2 mod 10. All right, those guys are actually the same. So really this statement equaling 0 really is the same thing as 2x is congruent to, so just a second here, just so we can get that, so you can see that completely. This is 2x minus 2y is congruent to 0, and that's the same thing as saying 2x is congruent to 2y. So really, we could say, so 2x is congruent to 2y. Okay, so 2x is congruent to 2y. What does this mean right here over here? Well, this means that 2y is congruent to z. Wait a minute. 2x is congruent to 2y, and 2y is congruent to 2z, and this is already an equivalence relation, so it's already transitive. So we're kind of going to borrow that one to say 2x is congruent to 2z, and 2x congruent to 2z is equivalent to this statement. So we're good. Okay, so we've shown it. So we've shown transitivity. All right. Okay, so we've done that. Now, how could we have done this a little bit more simply? All right. Okay. Under the assumption that if we have a partition of a set, that will give us an equivalence relation. Well, if we think about this, we just saw when we were looking at transitivity that really the statement was the same thing as 2x congruent to 2y mod 10, and that is the same thing as x arrow y. Well, if you notice this is like the output of a function where we're going from the integers and we're going to z mod 10z, and perhaps we have, and we have a function like x is sent to 2x bar, where this bar has reference to a chunk in this quotient right here. So x maps to 2x bar. Now, if we take a look at this, really, so if this function, we'll call this function f. Okay, so this is the statement right here that two elements map to the exact, so both x and y are mapping to the exact same place in f. So this is like f of x is equal to f of y. Well, that's the exact same thing that as saying that x and y are in the exact same fiber of f, which is just the fiber over 0 bar, the preimage is 0 bar. They're both in that. And the fibers of a function partition the domain. And so, of course, this, saying that, let's see. Oh, I guess, let's see, they both map, no, they don't both map to 0 bar, sorry. But what I mean is they're both mapped to the exact same thing. So call this C. I'm sorry, I said that wrong. So excuse me, little blunder on my part. Okay, so I meant that. Okay, so x and y are both in the same fiber over C, right? Whatever they map to. All right, so that looks a little better. Okay, so then we have the statement that they're in the same part of the partition is which chunks up the integers as a partition, so they're non-overlapping. The fibers are like in a fiber box diagram or just separate from each other. That makes an equivalence relation right there. So that's another way of saying it. And then we're through. All right. Thanks for watching.